Hello, my people. I hope you are doing well. I hope the test was easy for you. Hope things are going smoothly. As promised, there's going to be a couple of videos on u-substitution, which is what we talked about on Tuesday. This is 5.5, and I think the official title is something like integration by substitution. It could be called substitution rule, should be called substitution method. It could affectionately just be called u-sub. It doesn't really matter. They all kind of refer to the same thing, which is what we're going to be doing. And the whole idea is, of course, the undoing of chain rule differentiation. Okay, so remember that if I am differentiating a composite function, right, I have to identify what is inside, because when I differentiate, I have f prime of g of x, remember, derivative of the stuff times the derivative of the stuff, okay? When you're undoing the chain rule, you need to basically have both of these pieces represented in the integrand, or at the very least, it needs to be basically just a simple change in form, simple multiplication to getting you to this point. So let's go ahead and let's start with a problem. Let's go from 0 to root pi of x cosine x squared dx. Okay. Now, and the thing is that once we get a little bit more comfortable with the procedure and the method, you'll start seeing these things without asking yourselves these questions that I'm going to be running through. But for the time being, let's go ahead and walk through those questions. What is this the derivative of? What is my u? Or in this case, what is my g of x? When I'm identifying the g of x, the inside, that is what we need to basically need to use that to identify the u. Now, obviously, when you have a trig function, or you have a logarithm, or you have a radical, oftentimes it is the angle measurement of the trig function, the argument of the logarithm, the radicand that is the u. And the thing is that you can always sort of play around with it a little bit, because if you get your u wrong, you will get a du that either requires too much or too little from the rest of the integrand, okay? But for the time being, let's go ahead and identify x squared. Let's say, okay, well, if u is x squared, what is du? And of course, I'm just taking the derivative and then multiplying both sides. I'm getting du dx and multiplying both sides by dx, so it's not a derivative, it's a differential. And this becomes 2x dx. Now, if I have chosen the proper u, then I ought to either have du in this integrand, or I ought to be able to arrive at du by simple multiplication. And in this case, I can, okay? The only thing missing, and I'm going to go ahead and change the order of this so that it is a little bit easier to see. Basically, the only thing missing here, I'm going to have cosine of u. In order for this, however, to be du, it's missing that 2. And therefore, I multiply by 2 and by 1/2, so I'm functionally multiplying by 1. And at this point, I can now rewrite this as cosine u du. Now, here's the tricky part about doing a definite integral by means of u-substitution. These limits of integration were based upon values of x. So you have a choice. you can either integrate, change it back into x, and then plug in your limits, or you can change the limits to being in terms of u, and therefore you just don't have to change it back. So when x is 0, u is also 0. But when x is root pi, u is just pi, okay? So you have a choice on the definite integral whether to change the limits of integration into u, which I recommend, or you have the option of doing the integration, changing it back into the original variable, and then doing your evaluation. That winds up being a little bit tricky because you'll get going fast and you won't change it back. You'll plug x values in for the u, and that will be problematic, okay? That's why I suggest, highly suggest, that you go ahead and change the limits of integration from x values to u values. Now, we know that cosine is the derivative of sine, and therefore when I evaluate this, I simply need sine u from 0 to pi, or 1/2 of pi minus sine of 0. Now, when we're dealing with these values, remember that sometimes, even though there actually is area being accumulated, sometimes you just don't get an area because the positive area and the negative area cancel each other out. And in this case, this is 1/2 of 0 minus 0, or 0, okay? Now, let's go ahead and I'm not going to show you the graph. I will, however, go ahead and integrate it for you, and we'll use basically the original function, which is right here. Okay, I'm going to go from 0 to root pi of x cosine x squared, and then dx. Okay. Okay, and here's the thing. You got to remember that when your calculator does this, it is using algorithms that are not perfect, which is why this is 4.8 times 10 to the negative 14th. So basically, this is so close to 0 that basically we can sort of see how it might have slipped through in terms of sort of an algorithm that the calculator has. But basically this winds up being 0, and that is close enough to 0 where you should recognize it as 0. Okay. Let's go ahead and move on to another problem. Alrighty. How about let's do 0 to 1 of x e to the negative x squared dx. Okay. Well, again, it's probably your instinct should be the fact that, you know, whenever there is a variable expression in the exponent rather than just a variable, that's probably going to be our inside. That's going to be our g of x. That's going to be our u value. That's going to be our u expression. Okay. And remember, like I said before, if you pick the wrong u, you will get an unusable du, okay? So as I differentiate negative x squared, that becomes negative 2x dx. I look at my du, and I recognize from my integrand that I have all of the necessary pieces for my du. I have an x, it's right there. I have a dx, it's right there. I can provide a negative 2, so it's just as long as I also multiply by negative 1/2. So I'm going to go ahead, and like I did last time, I'm going to go ahead and reorder this so it basically looks a whole lot more like this. And I can go ahead and include a negative 2 in here, and then also multiply by negative 1/2 out in front. Okay. Now, once I've done that, I recognize the fact that this has been transformed into e to the u du. The problem is, of course, like I said in the last one, my limits of integration were in terms of x. Now they need to be in terms of u. So basically I say, okay, well, 0. If x is 0, 0 squared is 0, and then negative 0 is just 0. So it's 0. When x is 1, 1 squared is 1, negative 1, so I have a negative 1. The only problem here is the fact that transforming my limits of integration from x into u has basically messed up the order right here. But remember that all I have to do in order to fix that is multiply by a negative, and I can go ahead and flip those limits of integration. Because remember, every single definite integral is an implied difference, and all I'm doing when I flip those is I'm flipping the difference. A minus b and b minus a are negatives of each other, and therefore if I basically swap the order of the limits of integration, I simply have to take that negative 1/2 that was out in front and turn it into a positive 1/2. Okay? Now, it should be no surprise that that e to the u is the derivative of e to the u. So I'm going to do e to the u from negative 1 to 0, and I get 1/2 e to the 0 minus e to the negative 1, or 1/2 1 minus 1 over e. And that, of course, will give us a nice, neat decimal approximation. Let's see. I'll do it for you real quick. 1 over e. And our decimal approximation is 0.316. Okay, which should make sense, right? 1 over e is awfully close to 1/3, right? So 1 minus 1/3 should be roughly 2/3, and then half of 2/3 is roughly 1/3, and that's in the ballpark. Okay, so that gives us an idea that that is a reasonable value. Okay, now if you want to check it, okay, you can always, and let me make sure I don't get the shine. If you want to check it, you can go ahead and go 0 to 1 of x. Where's the e to the negative x squared dx, and when I integrate that, voila, I get exactly the same thing that I did when I did it by hand. Okay? Alrighty, let's go ahead and I'll go ahead and flip over to a new page just in case I don't have room for this next one. Okay. Let's do, what's that one? Looks like a fun one. Let's do arc sine of x over 1 minus x squared dx. Well, that's kind of annoying because that doesn't look as straightforward as ones that we've done before, right? When you are faced with something like this, and this actually winds up being pretty easy once you recognize what you need to do in order to change the form. What happens here is, when in doubt, go ahead and separate things. Okay. Okay, and once I've basically taken that numerator away from that denominator and left that denominator, the 1 over root 1 minus x squared, as its own thing, what I need to do is I simply need to recognize the fact that this right here is the derivative of arcsine. And therefore, if this right here is the derivative of arcsine, then maybe this is my du, which means that this could just be my u. Could it be that easy? Could u be equal to arcsine, and therefore du is 1 over 1 minus x squared dx? Well, if that's the case, then what we have here is we simply have u du, which gives us 1/2 u squared plus c, or 1/2 arcsine x squared plus c. And that is indeed the answer, okay? Now that's a little harder to see. If you had been given something like this, okay, where the arcsine of x was already in parentheses and something was being done to the arcsine of x, then you might have actually recognized it as u. But the fact that in your original one, it was by itself, that is what makes problems like this difficult. Not difficult to do, but difficult to identify, okay? And ones like this also happen, you know, you'll get a similar problem. It'll be natural log of x over x dx. And the key to solving this one is the fact that you need to pull them apart, just like I did in this one, and recognize, oh, well, that looks like du, and that looks like u. Okay? So it happens from time to time in a whole variety of different ways, with a variety of different classes of functions is what I mean. But you need to be on the lookout for the fact that sometimes it's not the argument of the logarithm that's necessarily your u. It might be the whole logarithm. It's not the ratio of the inverse trig function. It's the entire inverse trig function that could be your u. Alrighty, let's do one more. And this one actually should be relatively easy for us. All right. Like I said, oftentimes it will be the angle measurement expression of a trig function that's our u. So u here is e to the x, du is e to the x dx. I don't even have to multiply by anything. All of the pieces are there for me, and I get sine of u du. Recognizing I didn't take the time to write out the step of putting them together, but those two together are your du, and this right here is simply your sine u. Now once I have sine u du, I recognize the fact that sine of u is not a derivative, but negative sine of u is. So, I mean, if you want to go ahead and put a negative and a negative, that's fine. Or just remember that the integral of sine u is negative cosine u plus c. And I need to remember to go ahead and plug my original, the expression in terms of my original variable back in before I finish up. Okay? I'm going to go ahead and stop this first video right now. I'm going to try to do about 4 problems per video, and that'll make them a manageable length so that they're bite-sized rather than too long. But I hope that this has been helpful, guys. Please do let me know if you have any remaining questions on any one of these, and we will deal with those in due time. Bye.